Okay, let's talk about the relationships between different types of graphs in physics. Well, in kinematics, actually. So, first thing we got to get out of the way is let's just lay down the arena that this is going to happen in. So essentially, we're either going to have motion on a number line horizontally or vertically, or possibly up and down ramps or something like that where they might be at a slight slope. We'll just look at what that ends up giving us. So usually we'll have this, a 0 point, or this and a 0 point. Okay. Oftentimes this is going to represent objects being dropped. Okay, so sometimes the 0 is up high, sometimes the 0 is on the ground. But essentially, the only motion that we're ever really going to have to deal with will be either left and right on a number line or up and down on a number line. Okay? And we've sort of seen that before, and we've seen how we would graph position versus time. All right? But I want to talk about some specific scenarios. All right? So let's just take this to be our basic, where we're looking. So let's imagine that we have some accelerated motion now. And just to help us think about that, actually that's okay. We'll just leave it like that. There's really only two directions we could have a velocity in. Okay, either left or right. So we could have a velocity this way. Okay, and that velocity could be doing one of two things, right? It could either be increasing or decreasing, right? So let's imagine in the first case that we are applying an acceleration towards the right. Okay? We're applying an acceleration towards the right on an object that is moving to the right. So let's imagine it's a ball. Okay? And you come in and you start to push on this. Here you are. You're a powerful little critter. And you're pushing on this thing. What would you expect to happen over time as you continue to push on this ball? What would happen to the magnitude of its velocity? If it's already moving in this direction, what happens to the magnitude of that velocity as time goes by? It would increase, absolutely. Okay? And what we're talking about here, really, I'll just put it down here, we'll refer back to it, is this concept. If I'm having an object increase its speed, okay, like this little ball, right? The size of the ball, well, that's going to be the m here. It might get higher or lower. But essentially what we're saying is, in order to have that object accelerate, we need to push or pull on it. Well, the push or the pull is the force. Force is the push or the pull. This is Newton's second law, all right? And Newton's first law says that if we don't push or pull it, it's just going to roll along. It's not going to change how it's moving. It's just going to continue with a set velocity forever. That's Newton's first law, right? His second law says if we do start pushing it, how does its velocity change? Well, it accelerates. Okay, and his third law basically just says that I cannot push or pull it without touching, right? Without touching it. So we're just building on Newton's laws here. So I have a velocity in this direction, and I have an acceleration in this direction. The reason I have an acceleration is because I'm pushing it. So it should stand to reason that if I push something to the right, that's moving to the right, it's going to speed up, right? So velocity and acceleration in the same direction, that's going to mean speed up. So in this case, positive velocity, positive acceleration, we speed the object up. Okay? But we could also do something else, couldn't we? We could take this and we could have this guy move around to the other side, right? And we could have this ball moving to the right. Okay? I wonder if I can flip this guy. Yeah, there he goes. Okay. Now let's say the ball is moving to the right. Let's put him over here, actually. But he's pushing it to the left, right? So it has a velocity in this direction, but he's pushing it in that direction. So if he's pushing it in that direction, why did my velocity change color? I don't like that color. I want the I want to keep some consistency here. There we go. Okay. If he's pushing it to the left, all right, now my force is to the left. Well, my acceleration has to be to the left as well. And if something's moving to the right, but I'm pushing it to the left, the age. But if he's pushing it to the left, do we expect that object to speed up or slow down? Right, slow down. Absolutely. So let's just make a note of that. Slows. All right. That's fine. That seems to fit with what we think. If I apply a positive acceleration, something speeds up. If I apply a negative acceleration, something slows down. All right? But let's swap directions out now. Okay? So let's take this number line and let's take our values here. Let's take our little ball. Let's say now the velocity on the ball is in this direction, and our little man is pushing in that direction. So now we've got a velocity to the left, and we've kept an acceleration to the left. That's a bit different now, isn't it? So now we're moving left and pushing left. Will that object speed up or slow down? It'll speed up. And then, of course, last but not least, take him, move him to the other side. Now we have a velocity to the left, but an acceleration to the right. Okay, so now the ball's rolling left and he's pushing right. If it's rolling left and he's pushing right, does it speed up or slow down? Perfect. Is there any other scenarios you can think of here? That's it, right? So these are the only scenarios you could ever have. There's only 4 things that could be happening. Moving right and pushing right, moving right and pushing left, moving left and pushing left, moving left and pushing right. That's it. Okay? Now let's look at the direction of the arrow and just talk about positives and negatives. Here's a positive velocity and a positive acceleration, speeding up. Here's a positive velocity and a negative acceleration. That means slowing down. Here's a negative velocity and a negative acceleration. Well, that means it's speeding up, but to the left. And here's a negative velocity and a positive acceleration, and that means it slows down. Okay? There are no other options. That's it. Let's see if we can put these on displacement time graphs now really quick before we run out of time. So here, let's call this position and time. Now let's take scenario A here. Positive, positive. All right, so it's moving right and speeding up. Boom. That's what we would get. Okay? There's positive, positive. Now let's say we take the second scenario. Still moving right, but as it does so, it's slowing down. Boom. Like that. Moving right, but slowing down. Now we're going to do moving left, but speeding up. I'm not going to say where on this it is. We're just going to say what happens if we move left and speed up. That happens. Moving left and speeding up. And last but not least, moving left and slowing down. Like this. Okay? Notice how our slopes are either increasing or decreasing as time goes by. A decreasing slope, whether it be a negative or a positive, means an object's slowing down. An increasing slope, whether it be negative or positive, means an object is speeding up. Okay? Now we can take from those and we can look at what the velocity time graphs would look like. So I'm just going to squeak them in small size here. Increasing rightward velocity. Easy. Decreasing but rightward velocity. Well, our velocity starts high and decreases to almost 0. So like that. Notice it's always in the positive, so it's a positive velocity, but it's decreasing. Okay, here. Now we have a negative velocity, right? The object is moving to the left, and its velocity is increasing. So there, now we have that. And last but not least, our object is moving left with a decreasing velocity. So it's got to look like that. Okay, in the negative. Moving left, but decreasing. Okay? And I guess we could also put accelerations in here as well. really quickly. There's a positive acceleration. And here's a negative acceleration. Here's a negative acceleration, just as we expected from our initial diagrams. And here's a positive acceleration. Oops. Just that. All of a sudden I'm having trouble drawing my graphs. Positive acceleration. There we go. Okay. So how do we get from here to here, right? Well, a position time graph, the slope of that gives velocity. And here we have a constantly increasing slope. So we have a constantly increasing velocity. And then the slope of this gives me that. Acceleration equals delta v over delta t. Okay, so slope of that gives me that, slope of that gives me that. And going the other way, just to remember, rearranging these formulas, the area under here gives me this. So velocity equals a times t. A times t is the area under this graph. That gives me the change in velocity. And back the other way again, displacement equals velocity times time, the area under this. And you have to be careful with this one, because this is a changing velocity. So you have to use this version of it that we learned the other day, Vf plus Vi over 2 times t. Okay, so that's the relationship between all of these things. Now, I don't want you to get caught up in just trying to memorize this. I want you to think about the fact that all of those graphs are just simply an object moving left or right and being pushed left or right. That's it. This all just stems from that. If you keep it simple, if you build up one step at a time, keeping in mind that there's no reason to get overwhelmed because it's only one of these 4 things that's happening, okay? You can work out for yourself all of these funky graphs and how they all relate to one another, okay? And then later you can get to scenarios where you're actually like now putting 2 or 3 of them together, well, usually 2. So what if you had something like this? So you had a sloped ramp, okay, like that, and you take a ball, and we did an example of this recently. Okay. And you give it an initial push up the ramp. So it starts with an initial velocity in this direction. Well, what's going to happen as the ball rolls up? Will it slow down or speed up? Yeah, it's going to slow down as it rolls up a ramp. Why? Because the acceleration is pointing in which direction? It's pointing like that. And the reason there is this acceleration is because the force of gravity is pulling down here, but this ramp is essentially diluting that into a force along the slope, right? So as time goes by, this rolls up, it slows down. Why does it slow down? Because we have a positive velocity and a negative acceleration. Then eventually its velocity is going to drop to 0. So the length of this line gets shorter and shorter and shorter until it eventually gets to 0. And then it's going to flop direction. And the velocity is going to end up being in the opposite direction. Acceleration is set by gravity, so it doesn't change. It just keeps going. Once this gets to the top, as high as it's going to go, and its velocity is dropped to 0, okay, well, now its velocity is 0 here. Anything after this is an increasing velocity back in the other direction. And since acceleration is in that direction, it will speed up back down the ramp, right? Now all we have to do is think about, well, which graphs say that? Well, it's traveling up the ramp to the right and slowing down to 0. And then it's traveling left but speeding up. So what does that look like? Well, here's my position. Here's time. First part, okay, A left, V right, then V drops to 0 and switches direction, and we have speeding up back the other way that we came. Okay, so we get that. Our velocity. And all we're really doing is taking 2 halves of these things and clamping them together, right? So we take these things and clamp them together. So what's happening with our velocity? Well, it's positive but decreasing. Then it switches direction right here. And then it's negative but increasing, right? That should be one nice straight line. Okay. And then last but not least, our acceleration time graph from here. Okay, and just to finish off, essentially, to get this graph or this graph, we're looking at slope, right? Velocity is always the slope, the displacement time graph, and how we're getting these values is we're using tangent lines on the curve, right, to find the slope at various times. High positive slope, boom, that's this. Zero slope, that's that. High negative slope, that's that down there, and these are all the slopes in between. So V equals delta D over delta T. To get the acceleration, we're taking the slope of the velocity time graph. Well, this is much easier because it's just one continuous slope the whole time because the acceleration is not changing. And then if we were given this and we wanted to go back the other way, just like we said before, velocity is the area under the acceleration time graph. A times t gives me the area of this rectangle. And if we had a constant velocity, we could just say change in position is equal to velocity times time. But seeing as how this is constantly changing, we have to say this. And you kind of have to look at that in its proper context. So that first, then that. Okay? Because otherwise you're going to end up with a displacement of 0, which actually you end up with, right? So the object ends up back where it starts. So if you look at VF and VI, you get a displacement, overall displacement of 0 when you're done. And there it is.